updates are when they're due. No. Okay, so we're actually recording right now. All right, so this is the student's t-test. This is used to compare mean values measured by different methods. That's the overall definition of a student's t-test. You will notice that the student's t-test is actually essentially a statistical test, that it's the derivation of that test, okay? So what they've done and why this is the student's t-test is they've taken a statistical test that you would need to do some fairly complicated calculations to do, and they've simplified it into 3 cases, which gives them 3 sets of assumptions, right? And those 3 sets of assumptions have simplified the math down tremendously. In the first assumption, it's really tremendously. Like, this is trivial math, right? And then the second and third, not as much, but it's still simplified, okay? So keep that in mind when you look at these equations. Yeah, they're kind of longish, but actually there's something you could put in Excel and never have to put again, right? Which is actually pretty much what I've done in life. I'll be honest, I actually forget the equations and stuff for these all the time because I put them in Excel and don't do them for, until I teach this class. And that's what a good scientist does. Okay. So your hypothesis for a t-test. The student's t-test is going to be used to compare experimental results. There are 3 different cases that we must consider. These are the same 3 cases for the whole thing, but I have to talk about them as a unified whole. So you understand, they're all the same statistical test, okay? They're just assumptions we make to simplify things, okay? So the first case is that we compare a mean value with what an accepted value. This is actually true mean, right? But when we say true mean, please understand that that usually means a literature value or accepted value, right? A value that's widely accepted. Okay. This second case is going to be comparing 2 different means that you're getting from 2 different methods usually. And then the third case is actually going to be paired data. So you're going to compare the same group of samples using 2 different methods. They can also be different samples. We can have paired different samples. Samples are not duplicated in these, though. So let's look at this. Case 1, we measure quantity several times, obtaining an average value and a standard deviation. What we're looking for in case number 1 is, does our measured value agree with the accepted value? So we have an accepted value from a previous test. This is a widely accepted value, like the ones you look up for atomic masses in the periodic table, right? Or the ones you look up for in your book for melting points, right? And so you get your own value that is an average and a standard deviation. There'll be slightly different numbers. The averages could be the same, but the standard deviations are different, okay? Or vice versa. What happens if it's all the same? Your average or standard deviations between the 2 is completely, absolutely the same thing. Congratulations, you're done. They're the same, right? Yeah. I was going to say you messed up, try again. I mean, that's actually not a bad thought process to have, honestly. That's a good thought process to have. That if it's the same, be suspicious. If you knew that value before you started, you really should be suspicious, yeah. And you probably want to go ahead and do the test again if you have time. Because them coming up the exact same is actually kind of a statistical anomaly. That would be very unusual, right? I mean, even if you were to do the exact same test again that you got that literature value from, you probably wouldn't get the exact same results, right? Also, keep in mind that people get tricked all the time by the bad significant figures. They don't do the correct significant figures, and then they think they're different values. Okay? But they're not. If you actually took it down the correct significant figures, they're the same. I've seen actual studies by research groups that have done that. Okay. By the way, if you ever want to tease a physicist, tell them, so does it feel great to invent something that was invented 100 years ago? Because physicists thought they invented a new spectroscopy method called terahertz spectroscopy, which was invented by chemists almost 100 years ago and was called far infrared. And there was all these publications saying this was a new method, novel approach. Now, they did do novel things later with it, so don't get me wrong. There was actually some really great research there, but it's pretty funny, right? Okay, so case 2 is we're going to measure a quantity multiple times by 2 different methods that give 2 different answers. Each will have its own standard deviation. Do the 2 results agree with each other? And that's what we're doing the t-test for, is do these 2 methods agree with each other? Okay? Case number 3 is sample A is measured once by method 1 and once by method 2. The 2 measurements do not give exactly the same result. Then a different sample, that we'll call B, of course, is measured once by method 1 and once by method 2. Your procedure would be repeated for n different samples. The more of those you have, the better your uncertainties will be, right? But keep in mind, the more you have, it's not a linear scale, right? So you got to cut off at some point. Do the 2 methods agree with each other? Okay, notice the difference between these 2 different cases. This is something people get confused about a lot, right? In both of these, you're typically using 2 different methods, right? But what we're looking for in case number 2 is that do the results agree with each other? What we're looking at with case number 3 is do the methods agree with each other? So this would be you get a result and you don't believe it from one of them. You use a different method that's well established typically, and you get another result. Do those results agree with each other, and which one is, do I need to do it again with another method and see if I get the same result again? Which one would be the correct one then? Okay, that's the sort of thing you would do. You're not sure the result from one method is agreeing with the other one, okay? Case number 3, you're going to get a number of these results, right? It's kind of like doing number 2 multiple times, okay? And so case number 3, we're looking at do methods agree with each other? This is typically only done a limited number of times. This would be the sort of things that you would do with like a round robin to test labs. Are there methodologies matching between these labs? Okay? Or you test technicians in labs. Are my technicians performing this method correctly? Or is one of them giving me bad results and not doing this method correctly? Does that make sense? Yeah. This is looking at the methods, not the individual results. Okay? Does that make sense? Yeah. And case number 1 is really just trying to see if a result we got before that's an accepted result matches the other one.
So this isn't necessarily with it could be with multiple different samples, but it's more so like you take a sample and then you
case 3?
do it one way and then you take the same sample and you do it
different. Yeah, you would want to use matching samples in case 3. Yeah, and then case 2, you can do different samples. Yeah. You can even have 2 different sets. So you could have 2 sets of n. 2 different numbers of degrees of freedom in case 2.
By different methods, does it mean like completely changing how you did it?
We're going to do this. Well, we won't do the statistical part, but we're going to do this where we take a pretty much the same iron tablet, and we're going to examine its iron content in one method and then we're going to take that and do it spectroscopically. So we'll do gravimetric, spectroscopic. And that's the sort of thing you do. Yeah, exactly. And we could actually do a case 3, it's just we don't have time to do it. It would just take too much work to get all the samples matching, and yeah, with 2-hour labs, it would be a disaster. But if we had if I had all-day labs that I could do with you, that'd be awesome. Because it'd be a great demonstration of it, right? Yeah. I guess technically we could actually do that with a lab of people, you two. Because you're using, it doesn't, okay, so method can mean the methodology that you run the entire lab, but it can also mean, are these people using, if you're not sure if 2 people are using the same methodology, even if they're both trying to do gravimetric, you could use it in that case as well. It's, keep in mind that's, method is, typically, in that case, you might do like a case 2 first. Give them this, and see if they're agreeing. And then you might want to just run a gambit if you come up that they're not agreeing, and see if their methodologies match. Okay. If their methodologies match, they need to go back for retraining, right? And if you do it for a number of people, you can figure out who needs the retraining. Does that kind of make sense? So you always make a null hypothesis that is H0, 0 for null, right? And an alternative hypothesis, HA. Your null hypothesis in a t-test, student's t-test, is always that the differences are explained by random error. Okay? You don't get a choice. The alternative hypothesis is always that the differences cannot be explained by random error. And one of the most powerful uses for students' t-tests is it's a great way to figure out if you have systematic errors. Okay? Especially when you're looking at like lab-wide things. That really, really helps. So they all have sort of the same overall trend, okay? The same overall steps. You're going to calculate a t-value. I mean, duh, right? T-test, calculate a t-value. You compare t-test, your t-value, with your t-table. You're going to select a given confidence interval, or confidence level, and degrees of freedom. And again, those degrees of freedom and confidence intervals are the same as all the other stuff we looked at, right? Most places would have like a 95% if it's not, systems critical, and something in the 99% or above if it's systems critical or people are going to get hurt. Okay? Though those are good labs. There are many labs that are not good labs. 68% confidence interval. Anyways, so if your t-value is less than the t-table, you will accept your null hypothesis. Null hypothesis, what again? Yep, differences are random error, right? Okay. And again, that's at 95%. You'd be 95% sure that that one was your hypothesis, is, what it is. And then 5% confident that it is not. So, your t-value is greater than t-table. You're going to reject null hypothesis, and you would accept the alternative, which is the differences are not explained, cannot be explained by random error. And that typically means you have some sort of systematic error, or that your samples are not the same, or, there's a variety of things. This is why these are so broad, by the way. Basically, this narrows it down to a very small subset of things. It's random error. Okay, the methods are the same, the samples are the same, whatever, right? This right here actually is pretty open-ended, but remember that if it's not random error, typically it's going to be systematic error, unless you just are using the completely different samples. Okay? And you can usually tell if you're using different samples, right? So these are the equations. Again, this is method 1, method 2, method 3, right? So method 1 has a very simplified version. See that? Isn't that nice? Look at that, beautiful. Looks almost exactly like all your other equations, you know, doesn't it? Just has a t multiplying this s. Yeah, nice. So pretty. Okay, method 2 is longer and actually has 2 subsets to it, and it has sub-equations, like an equation to get you s pooled here. See that? And the reason for that is that in these cases, in method 2, your standard deviations are not from the same sample set. So you need to come up with an overall standard deviation that pulls those together. See that? Okay, method 3 again only has this one equation and is less finicky, but to generate the numbers in these equations takes Excel. You should do it in Excel, okay? It is not something I would recommend doing by hand with a calculator. It would take you far longer than you would want to take. Okay, so these are the sub-equations that you need to perform these equations here in method 2. See that? 49a, right there. Okay, so this right here is how you get S pooled. Can you guys go through this okay? I mean, it's not a particularly complex equation, it's just kind of longish, right? So you have a standard deviation for one set that has a number of, experiments that have been performed, a number of data, and then you have the second set that has a standard deviation in number, right? It does. It's degrees of freedom. You got it. It's not a derivative. Yeah. No calculus required in this class. All the calculus has been done for you, so you don't have to do it. Isn't that wonderful? All right. And again, same thing here. You get the idea, right? You have to come up with an overall number of degrees of freedom for 2 data sets that have different numbers of data points, right? So you couldn't come up with just a simple number. You have to do an equation. Can everybody read this okay? Let me know if you have trouble with this. It's not as hard as it might seem at first blush. And in fact, it makes a lot of sense when you start looking at it. Notice your errors were always like square root of the square of 1 plus the square of other. And you did the same thing with the number of data sets form. It's pretty much what you're seeing here. And notice that your degrees of freedom is -2 because it's 2 data sets. See that? Normally degrees of freedom are n minus 1, right? So it's actually pretty much what you'd think it would be. This is an example of case 1. So we have a coal sample. It's certified to contain 3.19% by weight sulfur. And we have a new analytical method that we measure 3.29, 3.22, 3.30, and 3.23% by weight sulfur for coal sample, that coal sample. We're given a mean by those values of this right here, which is the 3.26 and then, sub-zero, so we have that extra digit for calculation, right? All right, and we have a standard deviation given of this right here. You could have calculated those, but it's, not worth it. There you go. There they are. Does the answer using the new method agree with the known answer? So what is your known answer? What is your literature value what is your true mean in this case? Or accepted mean, that's actually the better term. Well, certified, right? Certified to contain. So it's that one right there, right? So what else do we need? Well, we're going to take the confidence interval, and we're going to take the mean. The confidence interval will equal the mean plus or minus our t-value that we have to calculate, that we have to get from our table, times s divided by square root of n. So what's s? That right there, right? What's this value, mean? Right there, right? Okay, notice that this never shows up in the equation. We're going to compare it to at the end. Okay? Where do we get t? Well, we need to know our confidence interval, right? So what's square root of n? Where will we get that n value? We count these, right? 1, 2, 3, 4, right? Okay. So if the known answer is not within the calculated 95% of the confidence interval, then the results do not agree. In this case, we're going to use a 95% confidence interval, which is pretty standard. Okay? So we would go to our t-table. We would get the 95% value for n equals 4 measurements, which would have how many degrees of freedom? 4 minus 1, right? Which is 3. So we look at our table. We go 95%, 3. We cross those values on our table, and we get a t 95%, so that's our confidence interval, equals 3.182. That's table 4.4, by the way. I would look in your book. I wouldn't look in my PowerPoint because it's much easier to read it in your book. Okay, so for the 95% confidence interval, our equation is going to be the 3.26 plus or minus our t-value, which is 3.182, times our standard deviation, 0.041, divided by the square root of 3. Ooh. Actually, I'm pretty sure that's wrong. Huh. Actually, I think that should have been 4. I'd have to double check your book, though, because it looks like my equation is not... yeah. Double check your book for me and let me know, okay? Should have been degrees of freedom in there? I'm pretty sure it's not. I'm pretty sure it's n, in which case it'd be number of samples. But I would like a double check. Anyways, this would give you this confidence interval. So we're 95% sure that this confidence within this interval, our value lies. Okay? And that's 3.26 plus or minus the 0.065. So if we set that as a range, we go ahead and expand it out as a range, right? We'd get these values here. That's this minus this value, this plus that value, right? What we'll do then to evaluate is we look at the accepted value, 3.19. Does it lie within these values here? Doesn't, does it? No, it's actually below our lowest value. And so what does that tell us? Well, we have a,
Isn't it 0.065 and it goes to 3/6 on the 3.195?
We're just expanding them all out completely, so we can be absolutely sure it doesn't lie within that. Okay? Technically, this would actually round up, yes.
Yeah.
And so it'd be even further outside. So we're for sure that it does not lie within that. Well, 95% confident that it does not lie within that. But yes, technically, you do not need to expand it all the way out to here. You could have this be 2.20, because it would round up to an even number.
By the way, in the book, they use square root 4, not square root 3.
Okay, so it's a typo. Yeah. The funny part is I actually get these examples from the book from the manufacturer again. So that I can just paste them in here supposedly. But apparently not, right? Because, see, it's a really difficult thing to edit equations for me. Yeah. So I'm supposed to get these correct from the manufacturer, but apparently not. I thought so. But it doesn't really matter, because that would actually give you a smaller confidence interval, right? Are the numbers different in the book?
No, they're not.
Okay, it's just that's screwed up. The 4 was actually used. Okay. Thank you for looking that up, by the way. Yeah, so it doesn't matter. I mean, we still get we actually find out that it's not us within our confidence interval period. It's actually even further out of it. Again, with these, you're probably better off going ahead and using the expanded values, the ones that haven't been rounded down. Because again, remember that those will introduce rounding error when you're looking at things. But you'd want to publish the 0.20, 0.32. Okay? And in this case, it won't matter at all, right? If you did find out, for example, the value without rounding would actually have this in its confidence interval, and the value after rounding does not, you'd be best off actually stating that, okay? That you'd be best off putting this confidence interval just like this, where it has the subscript 5, and showing these values right here, and then stating that this is within the unrounded value, but when rounded to the correct number of significant figures, it would fall outside of it. And so this value is probably within something very close to a 95% confidence interval, but may actually fall outside of a 95%. Like if you were to do a 94%, it might actually fall within, okay? And so it's less, like that 5% value probably isn't a good one of it being the case where they're the same value. It's probably higher than that, okay? Again, because that's our rounding errors. So what does that mean then? Well, there's 95% chance that these values do not agree, and there's a 5% chance that they do, right? Does that make sense? Okay. Again, the student's t-test can be used to determine and compare mean values measured by different methods. If the standard deviations are not significantly different as determined with an f-test, you would want to find the pooled standard deviation with equation 410 and compute the t with equation 4.9a. This is for method 2, by the way. I realize I don't have a label on here. So notice it has 2 sub-equations from method 2. See that? 4.9a, 4.9b. Okay. These are the cases where you'd use that. So the standard deviations are not significantly different. You would measure that with an f-test. You might remember the f-test from previous, where you can compare if 2 standard deviations are the same set or different sets. Okay. So you would find the pooled standard deviation using equation 410. Then you'd compute the t with equation 4.9a. And the easy way to remember that is that you have very close, very similar standard deviations, and so you can pool them together, okay? And that's going to simplify work down the line. Does that make sense? Okay. And so you can go the 49A, equation 410, 49A, to compute your T. And it's a little easier. There you go. If the T is greater than the tabulated values for the n minus 1 plus n2 minus 2 degrees of freedom, then the two data sets have less than a 5% chance, and that's what that means, by the way, P less than 0.05, of coming from distributions with the same population mean, meaning that they come from different populations. This can mean a few different things, but one of the more common examples of that is they're just not the same sample. Okay? If these standard deviations are significantly different, then you need to compute the degrees of freedom using the equations 410b, and then you would compute the T with equation 49b. Notice the B parts here match. See that? And again, these are ones where the standard deviations would not match. Okay? They're significantly different. And again, you can tell that using an F-test. I would highly recommend, if you need to use method 2, you perform an F-test on those standard deviations first before you do anything else. Okay? This is going to save you a lot of time down the road if you can manage to use the 49A instead of the 49B. If those standard deviations are similar, it's going to be easier in the long run. Okay? Don't fudge the number, though. Because if they are different, you will do all that work and get no results. Okay? Okay. All right, so here's an example of case 2. In this example, we have standard deviations that are similar. So we have a 36.14 and 36.20 millimolar. Are they significantly different from each other? So we were using one instrument, okay? And the instrument broke, went down, just recently got repaired, whatever, okay? And now we have a new instrument we have to use. But we need to make sure that our instruments agree. There's a variety of reasons instruments could not agree. Even if they're doing the same, even if they're both infrared spectrometers, even if they're both visible spectrometers, even if they're both GCMSs, whatever, right? Those instruments may not agree. Did I ever tell you guys the example of the $500,000 Raman spectrometer that was reading values that were wrong? That was not calibrated properly? So there's a group we used to work with, a very famous Raman spectroscopist, extremely famous, very, very prestigious guy, very prestigious university. He obtained a new type of Raman spectrometer that was $500,000 instrument. He bought it because it was supposed to come completely calibrated, and the company was really supposed to take care of it for him, so he didn't have to do as much work. He was, getting older. He didn't want to have to put in so much hours on that. And so he did we sent him a sample. He did a study on it for us. The results came back, and we're like, we have spectra of this. None of the numbers match. And so what we did is there's standards that you can get, and there's standards that are just freely available. They always come up with the same numbers every time, and they're extremely well known, okay? So we went ahead and sent them a standard and said, go ahead and run this. They were 5 wave numbers off on both sides of peaks for this standard, which is very bad, actually. That's really actually quite bad. Their instrument was totally miscalibrated, just awful. And they were pissed. They called up that company and, when you get your asses down here and recalibrate this fucking thing. Because they lost like a week of work. That they were all wrong. It was pretty bad. Anyways, so you always have to compare standards, you have to compare samples, you have to compare your different instruments. Like if you replace an instrument lab, you'll have to run this, okay? So you got two different means here. They're not the same number, right? Do those agree? Are the instruments actually agreeing, but you're seeing random error changing your number, right? Just a little, right? So you have two different standard deviations here, but these standard deviations are similar, okay? It's not like you're getting 1 and 0.1, right? So we've run an F-test. We found that these standard deviations are similar. These are our number of measurements here. Notice, by the way, this number has a smaller number of measurements, which it's not surprising the standard deviation is larger, right? For a smaller number of measurements. Well, yeah, makes a lot of sense. This happens a lot, actually, where your original instrument was much more efficient, faster instrument. It breaks, and you have to use one of the old ones that they decommissioned. Then you got to check if it still works, right? So the F-test indicates the two standard deviations are not significantly different. We can therefore use the T using S pooled. So we're going to calculate S pooled. That will allow us to calculate our T. I do not have the actual workout, do I? Shit. Damn. I'm missing. Okay, so we have plugged these values in, right? And please do that, I guess, at home. Let me know if you have any issues, because I don't want to, what time is it anyways? Yeah, I probably don't have time to do this and the case 3, do I? I mean, we could. Do you guys want to do this? Did you have any confusion about this? No, this value goes in there, right? This value goes there. This is the N1, N2. You'll get an S pooled value. And you just plug these in, right? Yeah. The hardest part about case 2 is actually figuring out which case you need to do. And just remember F-test, okay? The F-test says these two values are similar. Go on. Use the A, the set, that's pooled. If the F-test says that they are not similar, use the other method, because they're not, you can't pool them. Okay? Okay, so case 3, this is paired data, and you'll notice that's an Excel sheet thing, because honestly, I would never try to do these by hand. It takes forever. This would be hours of work. Nitrate concentrations in 8 different plant extracts were measured using 2 different methods. These are shown in column A and B, and you can actually see that this actually might be real data as far as I know. This looks like real data. So you have a spectrophotometry or spectrometry with a cadmium reduction here. And this one's an experimental biosensor that you just usually put the biosensor in, usually in a column or something, and detect it. Usually they work off of electrolysis. Remember the electrolysis stuff we talked about? We'll talk about more later, but yeah. So we're looking for, is there a difference between these two methods, or do they agree? Okay? And so in this, we're going to have matching samples for both. We make a sample, we use it in both methods. We make a sample, we use it in both methods, right? And so our number of samples are always going to agree, and we're going to have matching samples in both. We know the populations are the same, right? That's a fact. So the first thing we have to do is calculate the difference, one minus the other, right? There you go. And that's our differences right there. Then we're going to take the mean difference, which is just taking the average of those differences, right? This is why it's so much easier in Excel, by the way, is because you can just do this minus this, and then, you know, drag it down. Which really helps life. So then you're going to do the standard deviation of the differences. Notice it's really like the other ones, but you're doing it for differences, right? You see that? You're finding out if the differences are different. It's like a derivative, right? First derivative or second derivative of this. So you have a t calculated then. Again, you're going to use that formula that you're given for t calculated. Remember the case 3 formula on the bottom? You plug that in. This right here, by the way, is that formula expressed in a Excel cell, right? That's all that is, right there. Do you guys see how to read this okay? So these are the formulas in each of these. So there, D6 right there, right? And that same formula is in all those. And then this formula is that right there. This formula is that right there. Notice that's the correct standard deviation. There's 2 different types in Excel, so be careful. This is then the formula for this right here. This is how you do absolute value, by the way. ABS with parentheses around the value you want an absolute value for. Why do you need an absolute value? Because you could get a negative value, right? Yeah. This could have been negative. Okay. And D14, you can go up here, and that's the mean, right? Keep in mind these are differences, so getting a negative mean is not a bad thing. There's no problem with that, okay? It's very possible. That's how you do square root, by the way. SQRT, parentheses. Pi is PI, parentheses. You don't put anything in it. Anyways. And then you divide by D15 right there. And that's just the formula, as you've seen it before. Okay, and then D17 right here, that's actually this expression here. Notice it's literally looking the value up for you. Isn't that kind of cool? You guys don't appreciate that? You have an expression that looks the value up for you? You don't appreciate that? That's just sad. That saves you at work every time, man. How could you not love that? By the way, A13 here, because you numbered these samples from 1 to whatever it ended at, you can just use that. But you can also cheat here and do it differently, which is count A, highlight your entire group of samples if you don't label those samples as their number. And that would count how many samples you have, okay? I typically do that. I put count A here and then count my number of samples within this. Because sometimes you'll do like Grubbs tests and stuff, and sample 2 gets rejected. And then you'd have to relabel these if you wanted to do this properly, right? You understand what I'm saying? So if you do count A, it'll count up your number of samples, which what you want, instead of just relying on you putting samples 1 through whatever you actually end with. You understand what I'm saying? You won't necessarily use sample 3 that you took in the lab, right? And then your numbering can get completely fucked up if you do it that way. The way that the book tells you, okay? But it does work, but you need to keep really good lab notes to keep things in track. Okay, so for your given sample, calculate the differences between your methods, the average difference. That's what that means, by the way. See, it's mean of differences, D. SD is your standard deviation of the differences. And then that's just your number of samples, right? Notice you don't have to do any like S pooled and stuff because you have matching numbers of samples, right? They come from the same population for sure. Okay. And then this is your T value. That's your absolute value divided by. It's that same equation that's in the Excel sheet, by the way. This is your T table. And that is for the 95% confidence interval. You see how you express that? That's the uncertainty right there, the 0.05, 5%. Okay. T is less than T table. So you would accept the null hypothesis. If you're smart, what you'll do here is you'll actually write an if-then statement down here, and you'll have this change colors. If this is larger than this, it changes into a green or red, whatever color you want to do, and it would say null, right? So t less than t table would accept the null hypothesis, and that's how I always write these. So t is less than t table, it would then say null down here, or h null, whatever, h0, and then it would make that green. And I know the null hypothesis accepted, right? If you're going to be doing a lot of these, definitely put that in, because you are going to be tired and you'll forget. Okay? All the time. Removing outliers. You do not get to choose whether you remove an outlier or not. Okay? Let me show you an example of this. Is this any more of an outlier than this? See, there's value here, and this value here. Now, most people, if they look at this, will think that that looks like more of an outlier. Not really. This is probably just as much of an outlier as that one. And if you're making those decisions, then you're going to end up excluding this, and once you exclude these, you might exclude that one, and you're just going to continuously exclude things until you're down to, almost nothing. Okay? There's a really bad example of this in the lipid theory. Have I ever told you guys that? No? The lipid theory is the theory that says that increased consumption of lipids causes heart disease. And it was put forward by a person that looked at country data for countries. He originally got 36 countries. They're a random distribution. He got rid of all but 3. He should have used a Grubbs test, right? Yeah. And you know the ones he kept? I forget the third, but it was United States and Australia. They're the only 2 countries that have high fat content diets, but also are very sedentary. Yeah. If you look at like Northern Europe, they literally have holidays where they exercise, and they eat far more fats than an average American or Australian. So it's actually becomes pretty obvious that it's bullshit. But Harvard tried to prove it for 30 years because they got big government grants to do it. A lot of wasted money, but whatever. Okay, we'll pick this up next time. Yeah, you can see why this takes so much time, right?